Thank you. Appreciate that because I thought I remembered and I was happy and proud of myself and I didn't. Okay. Um, yeah, section 4 and 5 and so forth. We want to talk about, and it's a whole list of things. In section 3, you have dot product, and uh, you've got an assignment on that kind of stuff. I put some more assignments out there. I think I put assignments on 4 and 5, and I think I sent you an email about that before I decided I didn't care anymore. Um, and So in section 4, and I'm going to put it up on the screen in a second here. Just a moment. Share screen. Okay. Just to kind of go over things. The book talks about cross products in a certain way. I talked about cross products in a certain way. We spent a little time talking about, as you know, talking about matrices and determinants and stuff. The way the book defines the cross product, I'll get it down there in a second, is this triple. It's a vector, and it's A3B2 minus A2B3. And as I say, you can remember it if you want to write it out this way. Just remember 2, 3, 1, because 2, 3 is here, 3, 1 is second, and 1, 2 is third. So you have 3, 1 here. I'm sorry, 3, 2 here. Okay, I'll say it in a minute. 2, 3 here, 3, 1, and then 1, 2. And then the opposite, you can remember, you just switch them. And so you have A's and B's every place, but I just remember the first 3, and that's probably not how you'll actually do it. Now, so if I'm going to make up something here, because in the book you have exact exercises, and so if they want us to do a cross product, I'm just going to pick one here in a second. I'm doing a problem 2A, and I will show you what I'm doing here in just a second. And B is 2 minus 1, 1. Okay, so if we take A and B to be these two numbers, the way most people do a cross product is not to say this is A1, A2, B3, and B1, B2, B3, and then do what I said. Remember what I said a second ago is A2, B3, and so on. Most people don't do that. Instead, what most people do, and I'll try to explain today why, but they copy the A in a row, and they copy the B in a row, and then they do a determinant where they do an evaluation by the first row. So there'll be an I part, there'll be a J part, and there'll be a K part, which have to do with the I, J, and K here. The coefficient of the I will be the determinant you get. And as soon as I put a box around it, it kind of messes it up. So it's the rows and column that I is not in. I is in one column and one row. So it'll be things that you get from the second and third. So what most people do is they do 3 times 1, which is 3, minus, and you can do arithmetic here bad. Minus 1 times minus 2 is 2, and 3 minus 2 is 1, hopefully. That is how you compute the coefficient of the I. The coefficient of the J, you wipe out the first row and second column. So we're dealing with the 4 and the 1. That's 4. We're dealing with minus 2, and minus 2 is minus 2. Now, there's a problem here because you have to remember that whatever this was, you put a minus on it at the end. This minus is not something that is automatic. You have to remember to do it. Okay, and we can compute that. That's 4 minus minus 2. It looks like 6 to me if I didn't do anything wrong. And the last is when you do K and you wipe out, you look at these, that's minus 4, minus 6, that's minus 10. So we come up with I minus 6J, I guess, minus 10K. If you do it that way, And again, that's the vector 1, -6, -10. And the author uses brackets like this to talk about that. I don't care that much about it. I mean, I care, but everybody slops it down anyway. And so sometimes it's hard to tell whether it's a square bracket or a round bracket when you guys write. This would be, if I didn't make any arithmetic mistakes, this would be the correct answer to the cross product. Now, one of the things we're going to learn is that this thing is perpendicular to both of these. Now, that would be a way I can see if I made a mistake. So if I would take these two, the number A, and do this and do a dot product, that would be 4 times 1 is 4, minus 18, and plus 3 times minus 6, and plus 20. And I'm supposed to get 0. Now, I didn't get 0, did I?
You messed up on the J calculation, Professor.
I'm sorry?
On your J for your second value, the 4 is correct, but the negative, it should be -4 up there too.
This should be on the J. I didn't do this on purpose, but I don't mind having make a mistake because this is what kills us all on these problems. You're saying here it should be -4?
I think the second one should be, right? Because it should be 2 times -2.
Okay. This should be, this 4 minus should be 6. I don't see what's wrong here. This is a -2. That's be 4 plus 2 is 6. And you put a minus on it, so it should be -6.
I think it's that the -2 and the 2 should be multiplied.
I don't.
Yeah.
So what this should be negative.
-4, since 2 times -2 is
So I'm taking 4 times 1 and
2 times.
minus 2 times -2.
Yeah.
I mean, I understand, no, but what would you think I should do? By the way, I found out just now that the COVID has made me totally, my mind is gone. So I can blame it on that, not just on my usual stupidity. So if we have 4, I don't understand what's wrong. I honestly don't understand what's wrong here. 3, this would be -2. That's okay.
You're taking the J component times 2 instead of the I component times 2. So it's 2 times -2 equals -4. And that should go in the second thing of the J.
You're saying this is -4.
Yeah.
This is funny because you're saying I shouldn't take 4 times 1 and -2. I shouldn't do this?
No, we're saying that the 4 times 1 is correct, but then for the second component of that, the second half, it should be the 2 times the -2. So inside the brackets for J.
You're saying this should be -4.
Yeah.
Yay. Yes. So I was taking 2 times -2 about 10 times and getting 2.
Yeah.
Okay. Yes, thank you. So this should be 8. And this should be 8 here. And is it -8, I guess? And so now instead of that, we have -24 and +24. Okay. Now, so I am really amused at my own lack of 5th grade intelligence. But besides that, I did that because it's a good way to check to see if you're as stupid as I am. Okay. In other words, you can catch your mistake here because these things are very hard to see your problem once you've made it. So 2 different things I would do here. If I tried this and I did not come up with 0, I know I've made a mistake. In my own experience, like you just witnessed, it's very hard to find my own mistake. What I would do is do the problem over again. it is unlikely I will make the same mistake twice. It's harder if you've made the mistake to catch it, but it's easier to do it again and you won't make the mistake. And then you can go back and see where you made the mistake. I recommend that to you. It'll save a lot of time. In any event, if I would try the B now, I don't, in other words, this is not part of the problem, but because I'm shaky now, because it didn't work before, now I'm going to try this. This would be 2 and plus 8 and minus 10, and that's also 0. So the point is, if you have ways to check yourself, which is not to say you do the problem again, but to check yourself by some alternate way, I would recommend it. Okay. And so I'm adjusting something here, but that's a cross product, and that's all it is. That's all it involves. And as I say, most people do I, J, and K because it's an easy way, instead of saying A1 and A2 and A3 and so on and trying to remember, people do this. Now, so it's using a nice thing called a determinant, but the main thing is when you look at this, if I look at these three, and this is going to mess this up now, but the whole idea of a cross product is that this is A2, B3 minus A3, B2. And this one is the second one, and the other one is the third one. And so when you need to have some way not to worry about the first row if you want to find those three numbers. And as I say, you find those three numbers because they are 3 2x2 determinants. And so the IJK just makes it easy to do. And the IJK is useful for a lot of ways. Let's try to do this problem in a different way. Let's suppose I take 4i plus 3j minus 2k and cross it with 2i minus j plus k. Now, I'm not going to do it the same way. I'm going to do something else. Namely, suppose I were to cross I with j. Okay, suppose independently I want to do I cross j. Now, let's think about this a second. I is like 100. It's a vector that goes along the x-axis. 010 is a vector that goes along the y-axis. If I cross them, I get a perpendicular vector. What is perpendicular to 100 and 010? In other words, well, if you look into it, it's going to be the z-axis. Now, that doesn't mean that it's the same length. In this particular case, it will be length 1. But if you did this with I, J, and K, what would I put here? I'd put 100 and 010. And then I hope you see that when I do my stuff here, I'm going to get 0 minus 0. I'm going to get 0 minus 0. And for the K, I'm going to get 1. So what we learn with a little bit of work is I cross J is K. And what people do is they write the following little circle. Now, what we do is we learn a little circle here. And if you follow in a counterclockwise direction, any two of them will give you the third. I cross J will give you K. J cross K will give you I. K cross I will give you J. And if you go clockwise, it gives you minus. I cross K is minus J. So what some people like to do is to take this little table right here and go to a problem like this and say, okay. Oh, and by the way, what's I cross I? What's a vector cross itself?
Isn't that 0?
It's 0, yes. Somebody's in the waiting room, sorry, I gotta admit somebody here. Sorry, Andrew, I didn't see you. Apologize, Andrew, I didn't see you till this second. Anyway, I cross I is 0, J cross J is 0, and K cross K is 0. So if I wanted to multiply these two things together, you think about them like polynomials. 4i times 2i is 0. 4i times j is 4k, and when I put the minus in, that's minus 4k. I cross j is k. 4i times k, I times k is minus j. That's minus 4j if I didn't make a mistake. 4i times k is minus 4j. Now I've finished the I part. Go to the j part. 3 times 2 is 6. J cross I is minus k. 3jj is 0. 3jk is I, so that's 3i. And finally, the k minus 4, ki, ki is j. And minus minus is plus 2. Kj is minus I. And k is 0. So if I did it right, I have minus 4k and minus 6k is minus 10k. That's using up these two. I have 3i and minus 2i, which is I. And I have minus 4, I have minus 8j. And I think you'll see, if I didn't make a dumb mistake this time, I think you'll see we get the same answer. So some people do it that way. Okay? So that's the second thing I wanted to talk about. And I'm going to go back here to the other screen. So you see me again here a second. And let's go to this. Okay, so we go back to the book. There's some more stuff in this section. What you'll see right here at the bottom is what I told you about here, except he doesn't do a little circle thing, but he could. Most people do a little circle thing. They don't learn all this stuff. They just draw a little circle, IJK, and it helps you memorize it, or helps you remember it. And so we're making progress through the section. We have forgotten something though. On the previous page, there's something very interesting, I think, and that is that if you look at a parallelogram, it's going to turn out that the cross product has something to do with the parallelogram. Now, before we do that, what I want to do is to look at this theorem up here. Okay, and you can't see it right now, but you will soon. Okay. I hope you remember that the dot product between A and B was norm of A, norm of B, cosine theta. Well, it turns out that the length of the cross product is norm A, norm B, sine theta. So the dot product's length has to do with the amount, has to do with a number, but its absolute value will involve the cosine of theta. And the cosine of theta, if the dot product, if the angles are more than 90 degrees, the cosine is negative and the dot product will be negative. And so we usually say the dot product without the absolute value, because we get a number and we might want to know if the number is negative. And so we state it without the absolute value. But with the cross product, we state it with. Now, it's not absolute value. I wish the author would do it right. It's the norm. The norm of a vector is a number. And so this is not the absolute value of something. It is not necessarily positive. I say not necessarily positive, but it turns out to be, but not because of absolute value. This is actually a norm. It's the square root of the sum of squares. But it turns out to be this, and we don't have to have anything around sine, because sine is positive from 0 to 180 degrees. Now, this is based on the following proof. And what you really want to do is pay attention to this and this down here. The stuff in the middle is kind of laborious computations. And for most of us, we'd have to know where we're going to size this up right. So let me try to explain what I mean by that. If I take the norm of this thing is taking the norm of this right here. So what do I have to do? I have to take the square root of the sum of squares of these three things. The square root of the sum of squares of these three things. So this squared plus this squared plus this squared, I hope you see, that's a mess. Okay? It's like the expression, a bird in the hand. You may have heard the bird in the hand is worth two in the bush. You may have heard that. I like to instead say a bird in the hand is a mess. Anyway, the square root of the sum of squares here is a mess. And so what we do is we don't do the square root, we square the left-hand side, because that's just the sum of squares, and you can see that right here. But from here to the next line is a long computation, because I'm going to have several things here. I'm going to have these two things squared minus 2 times the product plus this. So I have 3 things here, 3 things here, and 3 things here. I get 9 things. And what the author has kind of done is he writes it out here, but then he cheats. What I mean by cheating is he knows already what he wants to do. If you guys were just trying to work this out on your own and you get these 9 things, it's like, okay, now what do I do? Okay, if somebody tells you, because what we do is we usually have a formula, it turns out that the square of the norm of the cross product turns out to be the squares of the norms of each vector minus the square of the dot product. And if you know that this is the formula you're heading to, when you get these 9 things, you can rewrite them, which he does, and then you can see this result. This is a famous result right here. But it's real difficult if nobody told you about what you're trying to do for you to take these 9 things and figure out how to manipulate them. Once you get that, then the whole problem becomes easy, because the dot product is, as we talked about a minute ago, the norms times the cosine. So the square would be the square of the norms times the square of the cosine. And I have the same thing in front here, so I can take out 1, and I end up with 1 minus cosine squared. And so 1 minus cosine squared is sine squared. So once I know this original formula up here, I can get the result. And that, if I take square roots of both sides, then I get this result up here. And so the norm of a cross product involves a sine of the angle. Now, that turns out to be important for what I said down here. Namely, the area of a parallelogram is also the base times the height, but the height is the norm of the second side times the sine of the included angle. So the norm of a cross product can tell you what the area is between the 2 vectors of the parallelogram. And that's kind of interesting. And so you'll have questions. Is the length of the cross product, or the norm of the cross product, equal to the area of the parallelogram? Okay, you can expect a problem like that on your test. Okay, now, so that's stuff we hadn't talked about before. And while I'm on that, on the next page here, we have properties of cross product here, which you need to look at. And we have what are called triple products, which sometimes are called scalar triple product. And that is the following. The dot product of A with the cross product of B and C turns out to be this 3x3 determinant where A is in the first row. And remember now that when we do play with the I, J, and K, the second part here is a cross product. And the I, J, and K, if we replace that by A1, A2, A3, then you'll see what this is. Anyway, you can write the determinant as a dot product involving a cross product. Now, the interesting about that is that if you go over here to a 3-dimensional picture, what's the area of a parallelepiped? In other words, a box. Well, it turns out to be the area of the base times the height. And I see that my moving around changes what you can see. I apologize. The height of the parallelogram is once again the cosine, I'm sorry, the length of the thing is times the sine. So it turns out that the determinant of a 3x3 matrix in 3 dimensions turns out to be the volume of the parallelepiped head that is determined by the 3 variables, not variables, 3 vectors. Okay, the only thing left in this section is torque. Now, remember that when we did dot product, sort of the last thing in the section was about the word work, W-O-R-K. The work had to do with the dot product between 2 vectors. The torque turns out to be the cross product between 2 vectors. And this explains, like when you have what are called right-handed screws, and you turn the screwdriver in a clockwise direction, the screw will go into the wall. And what the idea of using a wrench to do this is the wrench is in a plane perpendicular to where you want the screw to go. And so basically, we can deal with a plane, and the cross product of the plane gives you a normal vector, and basically that's where something is going to go if you're thinking about using a wrench on a or a screwdriver on something that you wish to penetrate into a 3rd dimension, and that like into a wall. Anyway, so you have the torque idea, where you have a force, and that's of course what you exert when you're trying to turn the thing. And you might have an angle involved here. And so we have a formula about torque. I think it's pretty easy to understand. We have a problem. Bolt is tightened by applying a 40 Newton force to a 0.25 millimeter wrench, and so on. Find the magnitude of the torque about the center of the bolt. And the author writes it out, and basically it's very similar to that work problem that was a section back. Namely, you find the norms of the 2 vectors, you find the angle between, and you multiply those together, the sine of that angle, and you will get the torque. So that kind of covers the section and sets us up for the next section, which is equations of lines and planes. So let's kind of rethink here a little bit. First of all, in my notes, I talked about lines and planes sort of, and if you've read through the notes, you know about that. We won't need equations of lines and planes really in Calc 2, but it's a good idea to learn about them so that when you get to Calc 3, it'll be easy for you. And so I want to do this section. Sometimes Calc 2 doesn't do this section, but I want to do this section just because we're all set up for it by what we've learned. In other words, dot products and cross products set us up to learn about lines and planes. So from the notes, we already talked about it. The idea of a straight line, you know about that in 2 dimensions. We have equations of lines, we have slope point formulas, we have 2-point formulas, and so forth. In 3 dimensions, a little different story. And so I developed for you the parametric equation of a line. And so in the book here, the book talks about that. And so he has a formula. Now, I want to talk about what we set up in the class. What I set up for you in the notes, if I have a vector A and a vector B, and so there's 2 points in the plane. Okay, hope you can see that. And I want to talk about the line that passes through those 2 points. One way to do this is parametrically, and that is, just a second. Excuse me, I had to sneeze, as you can tell. The line is the set of all points, let's say x, now that's a vector, such that x is, and there's a couple of ways we can do this, and so it depends on whether I want to use A or B as my main idea. And so I can set it up in this way. If I would take, now I'm going to write it this way, which is a little backwards. If I write the scalar multiple in behind it instead of in front of it, normally when we see like 2 alpha or 2a, we put the 2 in front, but in this case, we usually put it second. Don't have to. You can put it 1 minus ta if you want to, doesn't matter. Plus, now, as well, so let me do it that way. If I do this, add t times b minus a, so that's what you're used to, so. Okay, so if I have 1 minus ta plus tb minus a, and t is between 0 and 1. Now, if t is 0, what do we get? If t is 0, then this part wipes out, and I get 1 minus 0a, so I get a. So this set certainly includes a, because if t is 0, I get a. Suppose t is 1. When t is 1, I get the a part wipes out, and over here I get 1 times no, I'm stopped here. I'm stopping here because, once again, I'm confused. And this doesn't happen to me often. It must be interesting. I'll have to study myself here. When t is 1, this wipes out, and I get b minus a. I'm supposed to get b. Okay, so anyway, if I wipe out the minus a here, now I will get it. Okay, you'll understand a little bit why I said b minus a. Okay, so sorry, if it's 1 minus ta plus tb, I'm smiling. You can't see me smile, but this may be my last day. If t is 0, I get a. If t is 1, I get b. Okay, so probably I'll never put this on YouTube because I don't want you to use this in my trial to say how incompetent I have become. In any event, this is a line segment that goes through A and B. You can prove it's a line segment. I do that in the notes I gave you. Remember, that was to take 3 points and take point A and B and take a third point and show that there's a line between, that the distances make a line. Anyway, this is the parametric equation of a line. Okay? Now, you're going to see where the b minus a comes in very shortly. And that is, suppose instead of doing it that way, I decide to do it a plus t times b minus a. Okay? Suppose I decide to do it that way. Now I think you'll see why I got the two confused in my mind, which is confused today anyway. So what happens here? If I let t equal 0, what do I get here? I get a. If I let t equal 1, what do I get? T is 1, I get b plus b minus a plus a, I get b. So this also passes through a and b. It's also a straight line, which we can verify. So, as I say, I hope you can now see why earlier I got a little confused. They're very similar, except here, this is not the same as this, but you can take this and play with it. If I multiply this out, if I multiply the a times 1 minus t I will get this. And then I say, hey, notice I get exactly the other one. So these are exactly the same. They're just written differently. And only idiots like myself could ever confuse the two. All right, so this is what's in the book on page 1, page 8. It says Formula 1, page 864, except that he uses the vector v. Now, what in the world is a vector v? Well, to go back to his, when I take b minus a, what am I doing? I'm getting the name of the vector right here. Remember, when we have vectors, if I want to know what the name of the vector is here, I subtract the tail from the head. That gives me a vector at the origin, wherever the origin is someplace, and that will be parallel. Anyway, b minus a is going to spell out a direction. And what you want to do with a line is have a point and a direction. Now, b minus a is not necessarily a direction because it might not be length 1. So what we say is in the direction of v. If I want to actually make v a direction, I need to divide a vector by its length. So if I wanted to make this a direction, I'd have b minus a over the norm of b minus a, and that would create a direction. And then if I added here, what this does is it gives me a different way of writing the curve, because this might be length 5 and this is length 1. So by taking different t's here, I get different places along the curve. But if I'm trying to well, let me start over and say, if I would let t, instead of being between 0 and 1, if I let t be any real number, then I will not just get the vector, the straight line between these two, I will actually get the line that passes through the two. I get all the points. And if I do that, then this parameterization is different than the other parameterization, because the t here that gets me to a certain place would be different than the t here that gets me to the same place. In other words, if this is length 5 and t is 2, and this is length 1, t would have to be 10 to get me to the same place. Okay, so we have different ways of writing the line depending on how we wish to interpret the t we use. Well, that gives us motion along a line. And so we can use the idea of the length of this vector to change like velocity or where you are. And so if I want to have the thing go twice as far in the same time, I can put a 2t in here, whatever. So various things we can do to talk about motion, which is not our primary problem right now. But we get this vector equation I had, and if I separate the x, y, and z, now let me go back to my other drawing. What I did here, you'll notice I have a line under the x. That means it's x, y, z. It's actually a vector. I call it the vector x by putting a bar under it, and that would be a triple. So what I get with this equation is a triple, because I get an x, a y, and a z component, because this is a vector, and also this is a vector. So this whole thing has 3 equations. So what I get out of it is x, y, z. I get the first component of A, the second component of A, and the third component of A, plus B. In this case, if I try to separate it out, it's going to be B1 minus A1 and so forth, B2 minus A2, and B3 minus A3. What I'm saying is you get 3 equations in 4 variables. The A is given, the B is given, but the X, Y, Z, those are what we're trying to get as where we are, and the T tells us which point. So I've got 3 unknowns here and 1 unknown here, except that I stick various numbers in here to get the various numbers here. So each of these 3 things depends on T. So they're all functions of t, and we write one as a function of t, y is a function of t, and z is a function of t, like this, where I made functions out of those. And basically, a line is described, in this case, parametrically as 3 functions of t. Now, if I would solve for t, you know, when you have these equations, I can write t equals and put t in the other places. I can cut this down to 2 equations in 3 variables. And that actually is going to describe a line. A line always takes 2 equations in, if we're in 3 dimensions, in 3 variables. So this over here, the symmetric equations, is where you've done that, where you've solved for t in all 3 cases, and you can get, instead of the other way of looking at it, you can get these 3. I'm running out of time, so I don't really have enough time to talk much about that today, but I will later. And the other thing we get to is the equation of a plane, and I want to just spend a few seconds talking about that. We will elaborate on that on Friday. But a line is, and we talked about this the other day, a line is determined when we have a slope and a point. A plane is determined when we have a normal vector and a point. So what I need to have is some way of determining a normal vector to determine an equation. Or to put it another way, and to put it backwards, if I have an equation, when is that the equation of a plane? And the answer is the equation of a plane looks like the equation of a line with one more variable. So if I go back to the share screen a minute, if I have ax plus by and equals, let's say, d, say, people would stare at that equation and they wonder why I skipped c, but they scare us and they say that's the equation of a line. If I add cz, it turns out now I have the equation of a plane, not the equation of a line. As we've just talked about, the equation of the line is right above, and it's 3 equations as you've seen here, but it can be cut down to 2 equations, but you can't cut it down more than that. So planes are going to turn out to be what used to be the equation of a line. The generalization of that, you don't get a line, you get a plane. Now, it's going to turn out that A, B, and C is a normal vector. And that means a vector perpendicular to the plane. So if you have an equation, you can immediately get a normal vector. If you have a normal vector and a point, you can immediately get to a plane. And so what we do is we say, well, it turns out, and again, I don't have time to do it today, if I would write out what I'm writing out right now, if I have a point x naught, y naught, z naught, a point, and I would write out the dot product of the normal vector and x minus x naught, y minus y naught, z minus z naught equals 0. If you think about it, that says that this vector ABC is perpendicular to a vector written this way. We'll talk about what that means later, but if I let x be x naught, y be y naught, and z be z naught, certainly it would be 0. So whatever this thing is, it does contain x naught, y naught, z naught. And so what we have to convince you is that this actually is the equation of a plane. And the fact that the dot product is 0 says it's perpendicular to something. And you can read in the book, and I'll talk about it on Wednesday. I'm sorry, on Tuesday, we'll talk about this. Now, okay, it's 21 after, so it's time to take off the recording.